I wanted to try this cool proof of the Brachistochrone cycloid. Essentially, we have a particle, say a ball up here, and we have U, this is the potential, mgy, some height above this ground, I suppose, here. And we, at some point, we have some kinetic energy over here, which equals 1/2 mv squared. And what we're trying to do is essentially figure out what the path looks like, the equation of this path, as something falls from some y down to some point over here. And what's the fastest path, the path that we can take here that minimizes the time? You would expect it to be just a straight line or maybe just a slight curve, but there's a very specific equation that we need to find. So let's consider the equation for distance. That'd be something like x equals vt. And we kind of want to change this into like an s over here. So a ds. And then we're going to divide this by a v and call that equal to a dt. Of course, when you integrate both sides, this right side is just going to be equal to time. And this left side says ds over v. So velocity, we kind of have to solve for over here. We can say that the energy at any point is like u naught is equal to the kinetic energy final. Whatever we start with is what we're going to end with. And we can say that mgy is equal to 1/2 mv squared. And then that will just sort of cancel out these m's. And you get something like v equals the square root of 2gy. So that's kind of what we could put down here for v. Let's sort of set that up. But what about ds? Recall that ds squared equals dx squared plus dy squared. I just realized that if we have some y equals y of x, what we can do is we could take the derivative dy, and we can take a derivative there, and then we have to do a chain rule, so we get dx. So we can plug that in for dy over here. So we kind of get dx squared plus y prime squared dx squared. That equals ds squared. So essentially we can pull this out and say ds squared equals 1 plus y prime squared dx squared. All right, so it's clear that ds is equal to square root of 1 plus y prime squared dx. And that's what we can plug in right over here. So we're kind of going to do square root of 1 plus y prime squared. Here's the dx on top. And then we have to divide this by the velocity, which we found was square root of 2gy. So we sort of set this up as a little integral. Okay, this integral definitely looks terrible, but what if we called it a Lagrangian, this stuff right here? So we kind of have like a 1 plus y prime squared, call that to the 1/2. Then we have like a 2gy negative 1/2. Now, the Lagrangian is really powerful because you can actually solve integrals using the Lagrangian. Our idea is to sort of set the variation on the time to be equal to 0. And that's what the Euler-Lagrange is for. Let's realize that this Lagrangian is a function of some x, a y, and a y prime. But so the x is the base, so we have a derivative in terms of x for the base, and then we have to take the y prime along with your x. So you kind of have the derivative, partial derivative of the y prime here. We want to subtract at this point the y version of the partial derivative here, and so then we can set that equal to 0. It gets a little bit sloppy here, but we could subtract these two terms, set it equal to 0, and that is what we have on the inside over here. Ultimately, we need to realize something interesting here, because this portion says that we're taking a derivative in terms of x. Notice that the Lagrangian doesn't actually have an x inside of it, so we can use a Beltrami identity here. Beltrami identity, which means that we could say the Lagrangian minus y prime times the partial derivative of the Lagrangian with respect to y prime, and you can set that equal to some constant k. This is the Beltrami identity, and that's only useful if the Lagrangian isn't a function of k. Like of x. We don't have any x's in here, like explicitly. It depends on x because these y's are a function of x, as we claimed over here, but there isn't any x in there. So we can use the Beltrami identity, and with that we kind of just have to figure out what the derivative in terms of y prime is. So I guess we'll do that right here. So d over dy like this. It's going to be something like 1/2 times 1 plus y prime squared, and then you take the chain rule, that's 2y prime in there. You still have all this other stuff over here, 2gy negative 1/2. I forgot there's a negative half right here. So we did that. And so then, so that becomes a y prime divided by the square root of 1 plus y prime squared, and then a square root of 2gy. If we take our original Lagrangian right here, and we subtract it, so we go 1 plus y prime squared divided by 2gy. We subtract the y prime times this little derivative here, y prime divided by the square root of 1 plus y prime squared, square root of 2gy. Then we can multiply this side by 1 plus y prime squared, both sides, one top and bottom, so that way it's just multiplying by 1 on that side. Notice that this becomes sort of 1 plus y prime squared on the top. We would just get rid of the square roots. We could put this whole thing under one denominator, and then over here we're subtracting just the y prime squared, and then on the bottom we kind of have our two square roots, 1 plus y squared, and then there's a 2gy. Whoa, okay, so then this cancels out, and then this is again equal to the constant k. That's pretty cool. We could square this and also do the inverse, so that'll make it something like this. 1 plus y prime squared, 2gy equals 1 divided by k squared. At this point, we want to figure out what y prime is. So let's try to rearrange this. 1 minus y prime squared. Actually, let's make sure we keep the y here for a second. Divide the 2g on both sides so that we get 2gk squared here. This thing, I'm going to recall this like a new constant c. Just get rid of all of that. Now, we can say that 1 minus y prime squared equals c divided by y. And then we can sort of go y prime squared equals 1 minus c over y. And you take a little square root here. Boom. Kind of figured out what y prime is. I'd like this to be like a y over y so that we could put this under the same denominator here. And we kind of get y minus c divided by y. I'm crazy, this is actually supposed to be a plus right here. And so that this would be sort of a negative y plus c here. Switch this around. Anyway, let's realize that y prime is actually the same thing as dy over dx. So if we have this thing where we have a square root of c minus y on top with a y on the bottom, let's invert that, and we'll get something like dx over dy is equal to the square root of y divided by the square root of c minus y. Then we can put the dy on this side, and we've come up with a new integral. Let's write the new integral over here. We're going to integrate both sides. So we have x equals the integral of y, square root of y divided by the square root of c minus y dy. This integral looks crazy, but this is actually a really cool integral because let's set this equal to tangent. And if that's tangent, then that means that sine of t divided by cosine of t is really equal to that square root of y over that square root of c minus y. I mean, it looks like a tangent, right? You got the top and the bottom, you can divide it. Sine t over cosine t, we'll call it that over that. And if we start to cross multiply, we got sine t times the square root of c minus y equals square root of y cosine t. Then we kind of square everything, so we got sine squared t c minus y equals y cosine t. And we can rearrange this a little bit. Here we get c sine squared t minus y sine squared t equals y cosine t. This is squared here, by the way. The cosine squared. Right here, this is where we square things. Once we have c sine squared t minus y sine squared t equals y cosine t, let's put the y's on the same side. So c sine squared t equals y sine squared t plus y cosine squared t, revealing that y with a sine squared t plus a cosine squared t, that's just equal to 1. That equals c sine squared t. All right, now we figured out what y is. So we'll take our little dy here, and we'll take a little derivative here to 2c sine t cosine t dt. And that is what we can plug back into our integral right here, including the sine t over cosine t. So this equals something like the integral of sine t over cosine t, and then you have 2c sine t cosine t dt. That's our integral. Now this is looking much easier because we can cancel out these cosines, and then we get x equals 2c integral of sine squared t dt. Well, that's a pretty easy integral because it's actually x equals 2c. The sine squared becomes 1/2 minus 1/2 cosine of 2t. Boom. Now this integral is a piece of cake. So let's finish the integral here. We got x equals some 2c. We're just going to integrate this and it becomes t over 2. Then we have a minus 1/4. Actually, this is a plus 1/4 sine 2t. This doesn't look very good, so let's call it x equals c times t plus 1/2 sine 2t. Let's recall that we defined our y as c sine squared t, but that's also the same as saying 1/2 minus 1/2 cosine 2t. We're really close because we have our x and our y, but we should say something like theta equals 2t, and then something like c equals 2r. So when we do that, then we get x equals, let's say 2r in there, and then there's going to be like a theta divided by 2, so we could pull out the 1/2 there. So we're just left with an r, and we're left with a theta, and then we're left with a plus sine theta for the x, and for the y, it's just going to be the same idea. We're going to be r, and then there's a 1 plus, there's actually minus here, 1 minus cosine of theta. Boom. So here we have the answer to our integral, our solutions up here. Basically what we were again trying to find was the path that describes this curve here. And it turns out that, well, x equals r theta plus sine theta, and y equals r 1 minus cosine theta. So this here is actually the equation that describes a cycloid. And what that means is essentially like, say you have a ball that's trying to move around here, and the ball is rolling like this, and a point on that ball is the path that it's following as it tries to roll around here. So that is the cycloid, and that's the Brachistochrone cycloid, the path that a rolling wheel takes, a point on the rolling wheel. It's not the shortest possible path, but it's the fastest path, meaning the least amount of time. Interesting.